Okay, so those are kind of just some general ideas about what parameter estimation is and bias and what we want to deal with here. And so we'll start on to the first part of these two methods we're going to learn about, which are map and MLE. And actually, we're doing them in a different order. I don't know why I have them in that order. And these are two probabilistic ways to compute the parameters for the distribution that you're trying to fit your data to. So assuming you know what the data is, you want to fit a distribution to it, these are kind of theoretical methods that let you do it, and you can optimize it, and you basically get the best possible kind of parameter setting given the assumptions of these two methods. So they're two different approaches, but they're highly related. And a couple of algorithms for classification and regression come out of them, and they're kind of like these classic methods, but it's really one of the last things you can do for fitting. There's maybe one more after this where you're really optimizing to get the best value rather than searching for values that are as good as possible. So it's always a good thing to try, because if your model is simple enough, then you can get a very good answer and an interpretable answer, because you're talking about a distribution. So what we're talking about is we're having a probabilistic model of our data. So we have some data, D, and this later on we have X's, right? But the D includes X and Y, right? So it's got our input data and our labels are all inside that. And then we've got some parameters, right? So if we're talking about a Gaussian, then it's mean and variance. If it's Poisson distribution, we have some other parameters, but we're going to sample data from that. We assume that's what's generating the data. And we assume it's fixed, so we get these strong assumptions. Like, there is a distribution, we know what the distribution is, we just don't know what the parameters are, right? So that's the domain we're talking about here. Right? If you don't know the distribution, then you can't use this method. We're also still assuming that the data is IID, right? So it's sampled independently from this thing without any memory, like I said. And they're drawn from the same distribution. Oh, that's more of a definition of what IID means. And yeah, so what we're trying to do is to find out the best way to estimate these thetas. And best is not a universal concept. There's different ways to define best. So those two methods I'm talking about are two really standard ways to do that. So the first one, maximum likelihood estimation. We're trying to say that we want to choose the parameter theta that maximizes the probability of the data given that parameter, right? So this is the distribution that generates our data, right? So probability of, now I've got like 1,000 people that filled out the census form, you know, and I've got some nice distribution about all the variations. And so I could say, now, what's the probability of the next person that fills out the census form making above $80,000, right? You could actually make that probability distribution and estimate it because you've got some data and you know the parameters, right? If you don't know the parameters, we could say, well, we want to know what's the likelihood of all the data we've seen so far given some particular parameters that we give it, right? So if you expand this out, we're assuming, so there's no derivation here to require these two lines. The fact that since it's IID, this is just true, right? They're all independent. I hate this board. What we usually do is we maximize the log likelihood. Because it's better behaved. And my next slide, I have a kind of repeat of this in a different way, but this one's written nicer. So what we do is we take this likelihood, we're saying we want to know what the likelihood of that is. So it's just a log of that probability. So when we expand this out and apply logs in here, we end up saying that what we're really trying to maximize, right? We want to choose parameters theta so that we maximize this sum, right? So the log of the products is like the sum of the logs, and probabilities just add together. And so these are all kind of separable because they're under a sum. And so the thing we're trying to compute then is this formula where we're trying to find the parameters theta that maximize this, right? Where we add them together, right? Logs don't hurt us, right? Because all we want to do is maximize the probability. So even though the numbers will be different, as long as in a log it's increasing, right? So if something is higher in the probability space originally as a product, then the sum of the logs of them will still be higher. We can still pick the maximum, even though we're losing the true value of the probability here. The essential way this gets computed, and the kind of trick for this is, that's what the important part is, that we have to know a known distribution, right? So we know the actual format of the distribution, and then what we do is we take the derivative of that log formula we have, and we set it to 0, and then we solve for the parameter, right? So basically we're trying to find, right, the maximum point, and then what are the parameters that define it here, right? So you're taking the derivative of this distribution, whatever it is, and then setting to 0 and trying to maximize to that, right? So that's the trick. And then, yeah, if there's multiple parameters, you have to maximize them separately and solve individually. So anything else here that's interesting? Yeah, so as Yuhao's asking, do we need to know the format of the distribution? Yes, yeah, you have to actually know what the formula is, right? So for our Bernoulli, we talked about, we can do it because we have this distribution, and we could say, well, let's compute that, right? If you don't know, you just know it's distributed, you have to estimate it, then you have to use sampling approaches, right? And that's not what MLE is. So assuming you know the distribution, someone says this is a Poisson distribution, this is a Bernoulli, then you can use this method. I mean, maybe you don't know, you put a theory, you have a hypothesis, you say, I think it's distributed by this way, and I'm going to use it and fit it, and then you can check how accurate it is, right? So if we use our Bernoulli distribution as our underlying function, we're trying to compute that, and so, oh, we're just putting it out here in general. So this is an example where we've got 5 coins, and we have actual counts about how many times they've been flipped heads or tails. So we take the log of both sides. We have our log of our likelihood and our log of our distribution, and then we take the derivative. Right, so the derivative of this function gives us, sorry, I looked at this slide since last time. So once we compute it, okay, so we have the subtraction there, right? So we have we're taking the log of, well, the derivative of LP, which is this entire formula here. So we have 2 sums with logs, and right, and derivative of log p is 1 over p, I think, and we solve it down to that value. So we set it to 0, and then we can solve for this parameter p that we're trying to fit, which I had changed for some reason from theta. Yeah. And so in this case, once we solve it down, we end up getting this sum over all the x's divided by 5, right? Which is just the mean, right? So, I mean, we know what the answer is here because we solved it previously with the pure form. We showed that it was unbiased, right? To do that, using the mean was an unbiased estimator. So since it's an unbiased estimator, it's a good candidate to be something that maximizes the expected value of this, right? Right, so we end up kind of confirming what we had before, that we're getting this the sample mean of the data is the best one to use in this case. So we have another distribution, the Poisson distribution, So this is not talking about more of a process that happens over time. You're saying we're counting how many times something can happen. So you want to know how many coins are being tossed that way, or how many errors you should expect in your system over time, given something that's built on the system. It has this form, and so in this case, the parameters we have are lambda, which we're trying to estimate, and we do the same thing. So you just have whatever distribution you have, you take the log of it, you take the derivative and set to 0. That's what that is. You can look it up or solve it, and then when you solve for lambda and reorient, you get a new form. And this one is also the mean, but they're not all mean. So sometimes you do get distributions that are not just the mean of the distribution. But so it's not super complicated in a way. So as long as you know, it has a lot of assumptions because you have to have that method available. You have to have that, the distribution mathematically available, and you have to be able to solve it. But then you know that this estimator is going to be the one that maximizes basically the probability of the data that you have already, right? So it doesn't necessarily mean it's the best estimator. It just means it's the best, it's the most likely fit for the one you have, given the assumption of the distribution that you're using, right? If you're wrong about the distribution, or the data you have is super biased against it, it's missing something entirely, this estimator won't help you, right? But assuming you had kind of full knowledge, that would work. Okay. Does anybody have any questions on that part? Trying to have a later slide. Yeah, MLE formulas. I have. Where is that? Right after. So a later slide I have, which is kind of forms of some other distributions, right? So I should have a longer list. I should get a longer list for Bernoullian normal, for Gaussian, for Gaussian as well. It's mean, but for the variance, it's this kind of root sample variance. Okay. Okay, that's actually a better one to end on, because we other limitations. So yeah, it assumes that the form is known. Another thing is it assumes the uncertainty is explained by that parameter. Right, so it could be that you're right about the Gaussian, but there could be other basically features or variables inputting it. So it seems a very simple form of the thing. So there could be other sources of noise or dynamics in there that aren't accounted for in that one function. Yeah, and it's kind of just an approximation of that. So in this kind of method, yeah, the amount of data doesn't necessarily help. You improve it because you're just doing it theoretically. Okay. So the other form that we do is this map classifier. I'm trying to find my slide. Might only have one slide. Oh, okay. I'm in the wrong spot. That's why. Good. Okay, there's lots more on this. So we'll start on this, and then we'll kind of just introduce it, and then we'll continue from there on tomorrow's lecture. So the other flip side of that is just say what MLE is doing is essentially trying to find something that maximizes the entire distribution, the likelihood of any endpoint coming up. But what if you just really want to maximize a particular value? So another way to do it is just called this map estimator, so maximum a posteriori estimate. And this is saying that when we say posterior, remember we have the posterior distribution, which is what you would expect after you've seen the data and you've given the parameter. So we're saying, given the data that we've seen, let's just maximize the parameters to fit that exactly in a maximum way. So we use Bayes' rule to kind of flip around the distribution we have, right? Because the distribution that we've been sampling from is this, and what we want to estimate is this probability of the parameter given the data. But we need to kind of create estimators then for all the data itself and for those parameters on their own. And so we use Bayes' rule to kind of flip those around and come up with a new form to maximize these parameters where we're breaking down the prior and the log likelihood into two different parts and then maximizing. And this kind of becomes the basis of the naive Bayes classifier that we'll talk about as well. Somebody asked for the clarifying, so maybe I'll go back and clarify that, and that's where we'll stop. Improving with more data. I said that. So I guess I'm just saying that just know that we came up with this formula without using any data, right? So this approach doesn't, like most machine learning methods, once they're learning a model over time, you give it more data, you hope you're going to get a better estimate. This one, you're basically basing it on your assumptions and your understanding of the distribution. So getting more data wouldn't help you come up with a better estimator inherently. Like the mean is going to be better if you have more data. So if the mean is a good estimator of it, then if you have more data, your mean is going to be better because there's less chances that small variations will help it. So I guess more data would help in that sense. But it won't fundamentally improve how the model works, which is how many other methods would work. So I guess it's not entirely true that data wouldn't help, right? More data is always going to help your statistical estimators still give you a good value, but they don't improve any kind of model in any other way. So that's good. Thanks for clarifying that. Any other questions? I'll kind of stop there and we'll continue with map next time. I want to go back and make sure I didn't misspeak with the previous thing about the data and the likelihood. So I'll start there tomorrow, and then yeah, but I'll post this one up tonight so people can look at it if they missed it. Is there any other questions or clarifications? I'll stay around for a few minutes in case people have other questions. But I'll stop recording here.